Welcome back as we continue our adventure in calculating pi. If you missed the previous lesson, it would be helpful to view that first before proceeding. Here's the infinite series we saw last time. We add the reciprocal of every odd number, 1 over 1, 1 over 3, 1 over 5, etc., etc., all the way to infinity. Notice every other term is negative. This is an alternating series. Here is another way you may see the same series written. The difference is in the sigma notation. I have changed the index from n equals 1 to n equals 0. That changed a couple of things in the right, but both forms express the same thing. If you need to convince yourself, just plug in n equals 0, n equals 1, n equals 2, etc., etc., and see what you get. Remember that negative 1 to an even power is positive 1, and negative 1 to an odd power equals negative 1. On to business now. Remember our isosceles right triangle? Tangent is opposite over adjacent by definition. Using the Pythagorean theorem and some basic angle properties from elementary geometry, we can see that tangent of 45 degrees equals 1. 45 degrees is equivalent to pi over 4 radians. By taking the inverse of both sides, pi over 4 equals inverse tangent of 1, as seen here. Thus far, I have told you the infinite series in the top line and expected you to trust me. Hopefully, I've convinced you of the truth of the second line in the past two slides. Both are equal to pi over 4. So the trick is to show that inverse tangent of 1 is equal to the alternating series. That will prove that this infinite series converges to pi over 4. Then you no longer have to blindly believe what I tell you about this. We saw in a previous lesson that the area beneath this curve from 0 to 1 is equal to pi over 4. If you missed that and want more details, feel free to check it out. Very soon we will see why that is. So pi over 4 is equal to inverse tangent of 1. It is also equal to the integral at the bottom of the screen. Combining those together, we conclude that inverse tangent of 1 is equal to the integral of 1 over 1 plus x squared from 0 to 1. This is an important connection. More generally, inverse tangent of a variable x is equal to the definite integral seen in the second line. This is true. However, to prove this part, we will work with the derivative. So take the derivative of the left-hand side and the right-hand side. The fundamental theorem of calculus tells us the derivative is basically the inverse of an integral, so that cancels out on the right-hand side. The result is boxed in red. Before we can prove that, just a couple more details. F of f inverse of x is equal to x. To convince yourself of this, consider the example below. F of x is x cubed. The inverse of that is the cubic root of x. So f of f inverse, in this case, is the cubic root of x cubed. Those operations cancel, leaving us with x. So what if we take the derivative of both sides? We're going to need the chain rule of differentiation for the left-hand side. This can be found in most standard calculus textbooks, so I won't elaborate here. In the final line, I have isolated what we wanted to solve for. This was done by dividing each side by the term underlined in blue. So this is the general expression for the derivative of an inverse function. How does that apply specifically to the derivative of inverse tangent? Well, we know from calculus that the derivative of tangent x is secant squared of x. That is underlined in red. Now just plug everything into the expression. How do we evaluate secant of inverse tangent? We need a reference triangle for that. Tangent of theta is defined as opposite over adjacent, x over 1, as seen here. By Pythagorean theorem, the hypotenuse equals the square root of 1 plus x squared. We define this triangle such that tangent theta equals x over 1. Secant is the reciprocal of cosine. It is defined as hypotenuse over adjacent. In this case, that is the square root of 1 plus x squared all over 1. This is simplified and boxed in purple. Back to this screen, I plug in that purple expression to evaluate secant of inverse tangent. But we had secant squared, so I square that purple expression. This just cancels the square root. Now I'm left with the derivative of inverse tangent is equal to 1 over 1 plus x squared. We have just proven that. I know there were a lot of details there, so if I went too fast for you to absorb them all, please go back and re-watch as much as you need to fully understand. Just to make sure we're all on the same page, this was an unproven link at the beginning of the video. Since then, we have used some basic calculus to prove why it's true. Now all we have to do in order to connect the dots is show why inverse tangent is equal to the alternating series, seen here boxed in red. That is done by using the geometric series. Plug in r equals negative t squared. Simplify. Integrate term by term. Evaluate at t equals x and t equals 0. Then we are left with the general expression in the bottom. This is a useful series expansion for inverse tangent. In fact, we used it for calculation in our lessons on trigonometry. Now I hope you have a better understanding where this comes from and why it works. All that remains is to plug in x equals 1. That gives us the result we wanted. Feel free to ask questions in the comment section below. I have anticipated that some of you may be a bit rusty on geometric series, so I prepared the next lesson to remediate that. Thanks for watching, and stay tuned for more adventure.